seems to work now. Okay. Let me get started. So, thanks everybody to stay late for this demo tutorial info session on MyoSuite. So, like did last year, prepare some collabs for code that you can review and look at to somehow reproduce almost all the info that I will share today. I will not go through the collab myself, but you can open and follow the.
We can collapse this to make it more visible.
Thank you. Cool. There is the link also to the collab last year. That is more beginner. This year, show a few more advanced things. So let me get started on. So the outline will be to first understand why MyoSuite, what makes MyoSuite different, or why we developed MyoSuite, and then show you two major use cases / scenario. One is the use of MyoSuite for movement exploration, and the other one is to use MyoSuite for movement reconstruction. So let me get started with why MyoSuite. Well, what we are after is understanding human motor intelligence. And human motor intelligence is the dichotomy of the central nervous system, brain, spinal cord, and the peripheral nervous system, muscle, bones. And through the activation of the peripheral nervous system, we can manipulate, engage, and interact with the world. And yet, this is the final goal of humans, is to interact with the world. But we need to understand how our control system, the central nervous system, managed to do that. Now, if we think about the world around us, think about something as simple as drinking a can of Coke. This is actually something pretty complex. There are different ways that we can grab a Coke. There are different parameters or conditions, the physical condition of the Coke that affects when we manage or handle a Coke, like friction, masses. Coke can be of different texture. The can have different texture, but also can come with different shapes. Now we need to consider all those if we want to understand how human intelligence interacts with those objects. And one way to do that is to simulate them physically. We cannot record all the possible data, so we can simulate them. And the advances in physics simulation led us to have physics simulator like MyoSuite that actually allows us to do many of those things. MyoSuite has been designed for robotics with a real sim-to-real kind of mindset where it can be fast, accurate, and scalable, but it also has the possibility to have soft contacts, have deformable object, and also hardware acceleration. Because if we want to consider the world interaction, the real world interaction, we need to scale, to have a massive opportunity to scale and to understand all the possible conditions that we can engage with in the world. Okay, so we have a physics simulator for the world. What about the peripheral simulation? Well, biomechanics of the peripheral is much more than just bones and muscle, because this is a dynamics and non-stationary system. Muscle change strength. Muscle can come different strength and can change over time. In the short time, we can fatigue muscle when we perform movements. Our body changes masses over time and actually can change also the characteristics. We can get injuries. So we need to consider the peripheral when we understand how we are in the world, all those conditions together in order to create an embodiment that allows us then to understand how we interact in the world. And what we did is to leverage the amount of biomechanic works that have been done to understand how to model the peripheral motor system. We mostly refer to OpenSim work, plus we extended with other works. And what we try to do is to maintain as much as possible the same physics characteristics of the biomechanical model presented in OpenSim, preserving like geometries, moment arms, muscle forces, and we developed models they call MyoSim in MyoSuite. So that in addition to have all the characteristics of the same biomechanical models developed in OpenSim, now we can get speed. In early simulation, or still on CPU, we show that those models can be up to 4,000 faster than OpenSim. And we gain mostly contact dynamics. That is the way that our work will interact, our body will interact with the environment around us. So that's the most important feature that we leverage in understanding how our body interacts and connects with the world and affects the world around us. We have started a very simple model, the elbow model. We then developed a more complex hand model that allows us to study manipulation. We have recently released also legs model and the full arm models that allows us to manipulate objects in the space. All those models are open source, and you can find them at the links below. Actually, those models are pretty fast and can be also very lightweight. You can directly go to this website, and you can experience live on your browser those models live, where you can activate the muscle and see the effect of the activation of the muscle in the motor behavior. Now we have an embodiment that we can use to act and interact with the world. We can focus on the controller, on the central nervous system. And this is where our focus is. We want to generate controllers that allows us to replicate human intelligence. So we need to understand goals. We need to be able to develop and decode goals. We need to develop learning where we build understanding and knowledge over time on the top of each other. We need to have a system that is able to adapt to the environment continuously and also is able to generalize to what we learn to new conditions. And this is exactly why we create MyoSuite. MyoSuite is a collection of environments and tasks to be solved by musculoskeletal models, simulated in Mojoko, and made it very easy to use through an OpenAI API. We'll come in a second. This is a platform for developers, but we try to keep the level of understanding for utilization very low. You'll see in a second what I mean for being very low, but it's a development platform. It's not a UI platform. It's something that we need to use to build our control system, not just to use it. You will find more information on the website link below. So what I mean that is easy to use. So first of all, you can use it on any platform, Windows, Mac, or Linux. And what you need is just to have Python. That comes already pre-compiled in most machines. And if you have Python, you just open a terminal, you run pip install MyoSuite, and you have access to the whole suite of models, tools, and utilities that are needed in order to control the musculoskeletal models in the world. Let me move to some use cases, how we use it. Let me start with exploration. This comes with the idea that in order to learn, we need to experience and interact with the world. So we are agents that learn by interacting, goes with a purpose. So keep this in mind for understanding this section. How do we do that? We just need to follow 3 steps in order to completely interact with the environment. First, we need to import this gym adapter that allows us to interact with this with the platform. Then we need to create an environment. We provide a list of environments already that is a composition of a word, a musculoskeletal model, and a task that we need to solve. Then we need to control the musculoskeletal system in order to achieve the task in the environment. In this, we are the agent that acts in the environment through the muscle activation. So what does that mean? That we control, our agent is our controller, our brain, controls the model, the musculoskeletal model through actions. And every time we act in the environment, we receive a change, we change the state of our environment, our body and the environment. We can observe that, and we have information also about how far away are we respect to the target, our goal, and that is codified as a reward. And this happens just in another line of code with a 3rd step. You just need to do an n.step, the action that is the amount of muscle activation that you want to input to the model, and you are able to change the state of the model. Now you're in full control of the environment that you can act on. What means that you now can start learning from the environment. One of the most common ways to learn from the environment is through reinforcement learning, by trial and error. And you can use one of the libraries where you just need to do 2 more steps. First, you have to choose the algorithm that you want for learning. In this case, you can see in this line, we choose PPO. Second, you need to launch the training on this model. 2 steps. And you then are able to learn, for example, this random reaching of the model. Now, those collection of those 5 steps is all you need to learn different tasks. And this can be very different tasks, from picking an object to put in a basket, to a chase tag, to learning to manipulate a whole variety of different objects in the space with different maneuver, or perform locomotion in different conditions, like on staircase, on diagonal walking, on uneven surfaces, or even up and downhill. So we have, this platform is somehow compatible with most of the reinforcement learning frameworks. We have tutorials to show you how to use the most common, that is stable baseline, torsion-RL, DEP-RL, but in principle, the platform through the GIM API can be compatible with any other reinforcement learning framework. We provide somehow more than 300 tasks to be solved. But this is just scratching the surface of the variety of tasks that you can solve through musculoskeletal model. But I want to show you how simple it is to add the tasks. So once you have a task, for example, you have a hand pose, the task is to reach specific position of the hand, you can simply add a new task, for example, a rock sign. This has been a task to reach the posture of rock sign that has never been developed before. What you need is just to say what is your final posture, and you basically encode the new condition as you want to reach this new posture, and then just, again, running this, the reinforcement learning on the top, you can learn to achieve this goal. What I want to show you are those yellow surfaces. Those yellow surfaces are the contact surfaces that simulate the skin of the hand, that allow you to simulate the movement without having penetration of the fingers inside each other. Because those are collision surfaces, is like when you touch, your skin touch the extremity of your hand, that prevents the movement to self-penetrate and interact. So there are constraints on the learning that can be done. We can easily remove them, so you can highlight also in bright red the muscle activation that is necessary in order to achieve this posture. Now, as easy to add, you can add different tasks. For example, Jundan Park and Jundan Won at the Seoul National University add directional walking. So now you have basically an actor that can do all directional walking, like with a joystick. With the same simplicity, you can add different surfaces. This is just an uneven surfaces that the agent was trained to walk on, or you can just add other type of obstacle or condition or perturbation to the agent, like throwing balls, throwing objects to it. This is just to show flexibility to add or to change conditions. MyoSuite has been built for robotics and is as simple to add robotic actuations to those models. We have shown from the beginning how easy it is to add exoskeleton, for example, and to have a shared mobility with muscle and robotic actuators. More recently, Adam Dominguez-Ruiz from the Institute of Technology de Monterrey has developed a prosthesis, so that he's now learning, having agents learning to walk both with the muscle and with the robotic foot. We have also added from the beginning the concept that non-stationarity is in our model. So we have conditions that come by default about changing, dynamic change of muscle. For example, we introduce sarcopenia as reduction of muscle force, and you can just add this acronym, SARC, on the model, and you will get access to sarcopenic model with the reduced muscle force. For the hand model, we have added tendon transfer. With the referentation, you just need to add ref, and you will get a tendon transfer, one of the most common tendon transfer, that is the rerouting of the AP muscle into the thumb muscle. And we have added from the beginning fatigue model that you can add also with the MyoFati, but more recently we have released a new muscle model, actually this week. And I just want to mention why this model I think that is better, because it's a much more complete model. It's a three-state model that allows you both to consider fatigue, but also to consider recovery. So when you rest, your muscle recovers from the fatigue. And it's a continuous balance between rest and activation, so that when the muscle is activated starts fatiguing, and when it's rested, recovers from the fatigue state. So this is an example, thanks to Florian Fischer, who has been leading this, the integration. On the left, there is a model with a fatigue muscle, on the right, non-fatigue muscle. And the task is to hold the arm towards the point in green. So on the left, you can see the fatigue muscle that over time loses muscle strength. And when reached to the maximum fatigue, is not able even to lift any longer the arm. But after recovery, is again able to lift the arm, but again, fatigues again. So it needs to recover in order to continue the process. Now, we use this example to say that this is a fully observable system. You have access to all the information, all the forces, and any position of the body during this task. And just in the example of the fatigue, you have access to the muscle activation over time that you see on the top left, blue, the desired activation, on orange, the fatigue model. You have access to John angle, of course, over time on the upper right, the muscle length over time in terms of one muscle brachioradialis, and this is the muscle length that during the movement. And on the bottom right is the percentage of fatigued motor unit expressed as a percentage of maximum voluntary contraction. Okay, now, most of the time, we have a trajectory that we want to follow. And this can be used for imitation learning if we want to start bootstrapping some learning, or we just want to reproduce a trajectory of a subject. And this is something that comes to be very easy to perform and also very efficient. We have had Andrea Prestia, who has developed a really nice tutorial to show how simply can be done an inverse dynamic model. On the left is the target model, on the right a reconstructed model. You can see that just with inverse dynamics, when you have trajectory to follow, it's possible pretty easily to reconstruct that trajectory through muscle activation. And you can do this with all fingers, or posture, or conditions. But actually, just to show why this might be also relevant is that this system by design is meant to be highly scalable and efficient. So recently we have done this proof of concept with Delsys that has generously provided us some wireless EMG data. So this is basically, it can be a live muscle reconstruction, posture reconstruction to muscle activation. So in this case, muscle activation recorded through these electrodes were fed directly in the MyoSuite model in order to flex the elbow. And you can see on the left, the subject wearing the electrodes, on the right, the simulation of the elbow flexion, in the center, the muscle activation that are recovered through this modeling. Again, this is thanks to Andrea Prestia and Jonathan Hagyard at Delsys. Now, talking about reconstruction, motion reconstruction, one of the most intriguing things that humans do is hand-object manipulation. And we want to really provide tools to understand, replicate, and study hand-object manipulation. So those models are very easy to be spec'd. So these are just the line of code that you need to just reproduce this motion. And this is a motion that includes both the hand movement, but also the hand-object interaction in order to perform this manipulation. It's also very easy to change camera views in something that often have been asked about how to manipulate the visual scene. All this is present in the tutorial, so you can have a look how to simply change the camera position in order to render actions from different point of views. Now, once we have different objects and different possibility to manipulate the object, different trajectories that we record, we can start looking at all the variety of movements that we do when we manipulate object. This is actually the same, so it's the same object, but manipulated in a completely different way. Those are all trajectories that exhibits that type of behavior. But we can create a much larger data sets that allows us now to look at the complexity of human movements. And we released this data set is called MyoDN that consists of 50 different objects manipulating 90 different ways. So you can explore really how those trajectories can be recovered on different objects manipulated in different ways. So you will find many more tutorials than the one that I shared at the beginning on the MyoSuite repository. Please have a look. This is a community effort, so please share your feedback, your questions, or your suggestions. And I want to just summarize with the 3 major takeaways from this. First, MyoSuite is an open source project. It's really living for the community, by the community. Everybody is welcome to contribute, to participate, to engage. And it's meant to be a tool to study human motor intelligence. Now, this is only possible to achieve with a highly scalable infrastructure, scalable framework, and possibility to have extensible models, scenes, and tasks. MyoSuite comes with a variety of tasks, but any new task, any need, requirement is easy to add, and we welcome any suggestion to new tasks and new problem sets to be addressed. It also can be used for practical application. If you want to reproduce specific movements, if you want to look at specific muscle contraction, one of the most important results that we have obtained is really to recover how muscle coordination can evolve when you start looking to more complex actions, in the case of manipulation or walking. And it's just a tool that is available to start shining light on all these mechanisms. Again, I want to point you to a few links, the website, where you can find more information in videos of MyoSuite, the GitHub repository that is there for both for using the codes, but also to ask questions, address problems. And you can reach out to any of the MyoSuite support team for questions, suggestions, complaints, any type of feedback that you want to provide is welcome, both in the form of issue in the MyoSuite repository or directly reaching out to one of us. And I want to thank you all for your attention.
I need to mute someone.
Yes, but in the time, I have one question, Vittorio. Thank you very much for your demo first. So like in the last demo, you showed like this EMG-driven simulation. Was it implemented in real time?
Yes, actually, this is a tutorial that will be shared soon. We tried to do that before today. We managed to. It will be a tutorial that will be a streaming of DELSIS EMGs directly fed in the MyoSuite.
Okay, so how much is the time it's spent?
I don't know. Andrea has been leading this, but in one example that he has shown me for not with that, with another system was probably in the order of milliseconds.
A second?
Milliseconds.
Millisecond?
Yeah.
A couple of milliseconds.
Yeah, it was basically, it was completely real time. The system that was used basically was possible to be completely real time. So, and the system, I don't think that it was faster than 50 years, but that was, yeah, it was a different example.
Yeah, had you guys compared like this, like how to say, experimentally measured joint trajectories?
Sorry.
So have you compared like this experimentally measured joint trajectories with this reconstructed joint trajectories?
Not on this case. With DELSIS, we did for for other studies. So last year, we had a MyoSymposium near Reeves. Control labs and Meta was showing some results about exactly how to use EMGs and recover EMGs. Okay.
Thank you.
MyoSuite.
Any other questions? Yes, please.
Hi, thank you for the great demo. Just a question, is it possible to personalize the human skeleton model or for individuals?
Absolutely. We have a collaboration with James Cotton. I think that Vikash showed in the morning some results, but with James Cotton about using this full skeleton model, not the specific data showed here, but to personalize to different patients and disease states.
Okay, is it possible to personalize also like stroke patients or like some amputees or similar?
Well, not amputees,
Okay.
but for fully, without amputation subjects, it's personalizable.
Okay, thank you.
Sure.
Any other questions? So maybe just for the community, if they want to join this project, they can just help on the GitHub or.
Yes, we have a Slack channel that is very active to ask questions, to engage with the community. GitHub is the major destination for any issue, any request, any contribution. So we really welcome, in particular for the biomechanic community, to use, test, validate, and give feedback on the model. Again, our major goal, as I said in the beginning, is not about the biomechanic per se. Biomechanics is an instrument for us to understand the other mechanisms, so that is really welcome to get any feedback. We do our best to provide those models, but it's for the benefit of the community, so having any contribution is very, very welcome.
Perfect. So through GitHub, they can find contact information for more.
And the GitHub is here, the second link. This is the GitHub repository.
Yeah.
But anyway, you can send me an email, contact me. If you don't find information, I will provide them.
Perfect. Okay, let's thank Vittoria again. And the last demo today is about OpenSim Creator, which will be given by